Hello, and thank you for joining us for our attendees from all over the world. We appreciate it. My name is Sinan Kanatsis, Chief Executive Officer of KCOM, and today's moderator. It is my pleasure to welcome you to Meggitt's first in a series of webinars on transducer uses and best practices. In this webinar, we will review the effects that various mounting techniques can have on accelerometer performance. By the end of our hour together, you will understand how to avoid degrading the performance of accelerometers during their installation. Before we introduce our presenters, I would like to ask a question to the audience. Have you ever experienced an accelerometer mounting problem? In the next few seconds, if you can just go ahead and vote yes or no, we will share the results with you in a few minutes. We'll be closing the survey within 10 seconds. I'd like to now introduce our facilitators of today's webinar, Scott Mayo and Jim Matthews. Scott Mayo, an applications engineer with 25 years experience in the design and application of accelerometers, will explain to you the importance of resonant frequency before describing the test methodology. He will then review the results of the torque, roughness, flatness, and perpendicularity tests. Jim Matthews, an applications engineer manager specializing in customer support for piezoelectric acceleration measurement devices, will then review the test results for adhesive mounting techniques, including wax, and introduce a new mounting technique invented by Meggitt engineers before sharing conclusions. Scott and Jim will answer questions at the end, and we encourage you to submit them throughout the course of this presentation. There is a questions module at the top of your screen that we would like for you to submit questions throughout today's webinar. Recording of this webinar will be made available to all of our participants following today's event. At this time, I'd now like to turn it over to Scott Mayo. Scott?
Thank you, Sinan. So one of the most common questions that I've gotten over the years from accelerometer users is about how to properly mount or install their accelerometer. And of course, the sensor manufacturers such as ourselves, we do publish the ideal installation requirements, but you users, obviously, due to your limitations of your particular application, you've got to balance these ideals with the practical limitations you have with your specific application. So the real question becomes, what trade-off are you dealing with, or what trade-off are you accepting by not exactly following those ideal requirements that we publish? So that's what we're going to explore in this webinar, is when you vary those installation parameters, what effect does that have on the performance of the piezoelectric accelerometer? And in order to manage the data set that's generated by this amount of, or by this effort, we're going to focus specifically on amplitude response, and we're going to zero in actually in particular on mounted resonant frequency. So what is mounted resonant frequency? So there is a number of broadly used international specifications that define mounted resonant frequency as the point of maximum sensitivity in the sensor's amplitude response. So a piezoelectric accelerometer is a mechanical dynamic system. It's a mass spring, very lightly damped mechanical system. So as a result, it is going to have a resonant peak, much like you see in that graphic there. It's specified as a minimum, so the data sheet specification that we give you is actually a minimum. So what we're saying there is we're not going to ship you an accelerometer that has a resonant peak below that minimum frequency that we give you. So it's not a tolerance value that we target necessarily. We just make sure that resonant peak doesn't fall below the specified limit. And so in that sense, it's used as a rough measure of the upper limit of the sensor's bandwidth. And to give you just an idea of what values these may be, a typical accelerometer might have a resonant frequency of 20 kilohertz, although certainly we have many models that go much higher than that. So why do you care? Well, so for piezoelectric accelerometers, the resonant peaks are particularly high amplitude, which what that means is the sensitivity of in that region of the resonant frequency is many times the reference sensitivity. So what can happen is if you have vibration components in that region, they're going to be highly amplified, and potentially you're going to have distorted measurements and have corrupted data, which of course is no good. So as a manufacturer, we give you that specification under ideal mounting conditions. But of course, as I've said earlier, as a user, you're probably going to be dealing with less than ideal installation requirements that potentially is going to decrease the stiffness of that mounting, increase the damping of that mounting, and that's going to cause that resonant peak to move down, and thus you're going to have less bandwidth than potentially you thought you were going to have, and potentially amplify vibration components in a region that you didn't think you were going to have that happen. So that's really why that amount of resonant frequency and knowing where that's at is critical in your application. So what are these ideal installation parameters? So here's some numbers that we've published for many, many years for a threaded stud mount type accelerometer. We say you need a surface flatness maximum of 0.0003 inch total indicated run out, a surface roughness maximum of 32 microinch RMS, that the drilled and tapped holes should be perpendicular within a degree, that you should use the recommended torque, and ideally you should use coupling grease, or sometimes known as ultrasonic couplant or ultrasonic grease. And then for an adhesive mount accelerometer, we recommend that the bond line be as thin as possible, which essentially means apply some adhesive and press the accelerometer down fairly hard to thin that bond line out as much as you can. So the idea here, what we want to explore in this presentation then, is what happens when you vary all these things. What happens if you degrade some of these parameters? What effect does that have on the accelerometer's performance? So let's talk about some of the tools we used to explore this whole thing. So a lot of the work was done on the Endevco Model 2911 air bearing shaker that's shown to the right there, and to the left is a picture of the entire system with all the data acquisition and signal conditioning put together. So that was the major tool we used to collect all the data. And then here's a summary of the test methodology that we used, the accelerometer models that we used, and the parameters that we varied. So along the top, the 7704 accelerometer is representative of a bottom located stud-mounted accelerometer. The 2221F is an example of a through-hole center-mount stud-mount accelerometer. The 2222C is an example of one of our adhesive mount accelerometers, and then the Model 46A is mounted with the pod system, and we'll talk more about that later. And then along the side there, the parameters that we varied would be torque, roughness, flatness, perpendicularity, and then for the adhesive mounts, we did some variation on the wax, and then we used a number of adhesives to see how that adhesive mount accelerometer would perform.
So at this time, we would like to transition to our next segment and our next question. We would like to know, how do you most often mount accelerometers? If you can take the next few seconds to answer this slide, we do appreciate it. In our first poll, we learned that we had of 77 votes, of them. I'm just clicking up the results. We had 74% actually say yes, that they had had accelerometer mounting problems. Over the next few slides, Scott and Jim are going to offer some valuable insights into how to prevent those problems for both stud and adhesive mounting. Scott will start us off with the results of the torque and under torque testing.
Thank you. Yeah, so the first thing we varied was torque, and again, in the interest of managing the data set here, we simply did the recommended torque value, and then we did a 50% under torque. Values between there didn't necessarily show a dramatic difference. And one thing that I didn't mention earlier in the test matrix slide is that we varied some of these parameters, both dry, no material between the mounting surface and the accelerometer, and then also using that ultrasonic coupling material, which is the tube of material that you're seeing on the right-hand photo there. And of course, the torque wrenches is what we use to vary torque. And we got some very interesting results here. So let's take a look at those. So let me just make a few comments about this slide. So we'll be seeing a number of slides that look like this. So as I mentioned, we're going to focus in on the mounted resonant frequency region of the accelerometer. So this is the amplitude response of the accelerometer, only from 10 kilohertz to 50 kilohertz. The black bar, the black vertical bar you see there is actually the specified resonant frequency for this particular accelerometer, which for the 2221F is 40 kilohertz. So we want to see those peaks being above, to the right of that black bar. So let's drill in and take a look at a couple of these. So the first arrow you see there, the light green, that's the baseline. That's where we use the recommended torque, we use the grease, and we got a curve that we would expect. The resonant peak is above the specification. The curve, as you go lower in frequency, flattens right out down to about a 0 dB response variation from reference sensitivity. What's interesting, though, is the next curve, the red curve, where we went 50% under torque and used grease, and we got a very similar result, a result that I would say is acceptable. The resonant peak is above the specification, and the curve flattens out, fairly rapidly as you move lower in frequency. What's really interesting, though, is the light blue curve below that, the third arrow down, where we use the recommended torque and no grease. And I have a feeling that a lot of accelerometers are mounted that way and got what I would call probably not an acceptable response. The resonant peak is above, is to the left, I should say, is below the resonant peak spec. So in this particular case, even though we specify this accelerometer having a 40 kilohertz or above resonant frequency, in this particular installation that did not get achieved. So certainly not a result that one would have expected based on the data sheet, but this was simply caused by degradation of performance due to the installation. So a very interesting result. And of course below that, where we went 50% under torque and no grease, we got what I would consider a completely unacceptable response, where the resonant peaks damped out significantly. So the takeaway here is grease, using that ultrasonic grease really helps your performance here. And we'll see this again shortly. Well, here's the other, this is the 7704 accelerometer with very similar results as the 2221. Same thing. The two cases where we used grease, we got very similar performance. In the two cases where we did not use grease, we got unacceptable performance. As a matter of fact, for this particular accelerometer, in the cases where we didn't use grease, we actually got those sub-resonances in the amplitude response that you see there circled with the dashed line circle. So a response that probably most people would not have expected out of the accelerometer based on data sheet specifications. Again, caused by not the best installation. So let's take a look at what happened when we varied roughness. So the way we did that was we had a number of washers fabricated, and that's what you see on that right-hand photo there. And we inserted those washers in between the armature of the shaker and the accelerometer. It was mounted on top of that, and so we had a series of these washers made all the way from a very finely polished surface of 16 microinch all the way up to a ridiculously rough 500 microinch, and that's actually the washer you see there on the right-hand side. So you can see that it's a very rough surface. We certainly wouldn't recommend anybody try to install an accelerometer on a surface that rough. But let's take a look at the results that we got out of that. So again, we're zeroing in on that resonant frequency region from 10 kilohertz to 50 kilohertz. And so for the baseline, with the 16 microinch surface and with grease, we get the green plot there, the green line, very acceptable performance. But even with a 500 microinch rough surface, a very rough surface where you can see the machining grooves, we got what I would say is an acceptable performance. It's very minimal acceptable, but it meets spec because the resonant peak comes up just right above that specified point of 40 kilohertz. So with grease, even with a very rough surface like that, you got acceptable performance. Versus the next curve down, the red arrow there, with a 16 microinch surface, a very good surface, no grease. Again, you're getting that resonant peak to come up before the specified region there, so that the peak popped up before it should have. And then, of course, the same thing with the 500 microinch, no grease. So again, the takeaway here is grease does a lot of nice things for you. Even with a very rough surface like that grease really helps you achieve the performance you need. Let's talk about flatness then. So again, we did the same thing. We had a series of washers made up with varying flatness. So we started all the way from a very flat 0.0005 inch total indicated run out all the way up to a ridiculously not flat 0.1, and you can see that in that photo there in the bottom left-hand corner there. You can see what a curvature that thing had, and of course with the accelerometer mounted on it, that's a completely unacceptable installation, I would say, but we wanted to vary this thing all the way from very good to very bad. We would never recommend that you do an installation like that. But let's take a look at the results. So this is a busy slide. All 5 of the runs we did I'm showing here, but let me try to split this out for you here and show you some interesting results. So I'll split out the top 2. So this is an interesting result, not expected necessarily by us. So for the red curve, 0.0005 flatness, total indicated run out, of course we got the results that we expected. It's a baseline situation. But even with a flatness of an order of magnitude worse at 0.001, an order of magnitude worse than what we've been saying for many years, we got nearly identical performance. It nearly lays on top of it. So that's an interesting result that I have to say we didn't necessarily expect. But now let's take a look at the final 3 curves that we ran as the flatness got increasingly worse. So here's the remaining 3. So even at 0.01, the purple one there, would we say that's acceptable performance? It does have the sub-resonances there within the 2 circles. Certainly at 0.05 and 0.1, those are unacceptable performances. But is the 0.01 flatness acceptable? Maybe you could say that. Certainly, though, the 0.001 flatness was acceptable, and I think a very interesting result that leads us to conclude that flatness the criticality of the flatness that we've been saying for years maybe is not quite as critical as we had thought. Let's take a look at perpendicularity. So we did a similar thing there to vary perpendicularity. We used these mounting blocks, and for the top part of the mounting block, we drilled and tapped the hole at a perfect 0, and then at 2 degrees off, and then at 5 degrees off. So for example, if you look at the photo on the right-hand side there, that's 5 degrees off, and you can tell that the accelerometer is dramatically tilted there and barely making the mounting surface of the accelerometer is barely making contact with the test surface there. But interestingly, let's look at if you look at the photo on the left-hand side, that's a 2221F, so that's a through-hole center mount accelerometer. And even though the tapped hole is 5 degrees off, there's enough clearance in the hole through the accelerometer that allows the accelerometer to lie flat on the test surface. So, and that's going to be an interesting result we're going to see here in a minute. But just remember this slide here as we go to these next two results slides, and you'll see that this makes some sense. So if you look at the 2221F results at 0, 2 degrees, and 5 degrees, because that clearance hole allows the accelerometer to lie flat, we got nearly identical results with all 3 runs, even with the mounting hole 5 degrees off, which is significantly off. So very interesting result versus if we take a look at the 7704, even with 2 degrees off, we got a pretty bad result, I would say, pretty much unacceptable. So the conclusion that I think we can take away on the perpendicularity, that if you're dealing with an accelerometer like the 7704, where it's a bottom located stud mounted accelerometer, you really do have to have that perpendicularity nearly perfect, versus an accelerometer like the 2221F where you can drop that mounting screw through. You've got a lot of tolerance to vary that perpendicularity. And with that, I'm going to turn it over to Jim.
Well, thank you, Scott. I'd just like to say good day to all our webinar attendees. The presentation is going to transition more to adhesives and wax as opposed to the rigid stud mount accelerometers. Not all applications are going to be stud mounts. We have some lightweight structures and so forth that will have very small adhesive mount accelerometers. So that's where the focus is going to be right now. You can see on this current slide on the adhesives and the wax thickness, we've got 3,000s, 10,000s, and 15,000s thickness varied there. As you can see in the photo, it just allowed us to make a determination what the results would be on that. And as you can see from the next slide that we have some interesting results. The minimum wax obviously is the best, as Scott had mentioned before in the introduction, that the minimal amount of wax or adhesive between the accelerometer and the test article is the best way to go. As you can see, the resonant curve was up the highest with the minimum amount of wax. We also had 3,000s in there, and you can see the other curves up to 15,000s. As you got thicker amounts of wax, it did change the resonant curve somewhat, but not significantly. So it appears that we have to focus on the different types of adhesives as opposed to the thickness itself, although it is a determining factor, it isn't that significant. So what we'll do is transition to the next slide, and we'll look at the different various adhesives that I'm sure all our users are using at different times depending on their application and the type of test. So what we have here on the left is the petrol wax, which is easy to use and it's convenient. You can put it in your pocket, carry it around your test lab or wherever you're at without having to worry about dripping and taking caps off and so forth. That's probably good to less than 100 grams on unit for adhesion, 20 G's peak type of thing. The clean surface is what you want to look at when you're doing with adhesives. That's a focus that you want to not forget about is to clean the surface to get best adhesion and use maybe a solvent of some sort. The second picture is the Aran Alpha or Crazy Glue, and then we have the Loctite, which is a gel type of instant adhesive. Those are all pretty good and convenient, good adhesives for higher frequency measurements. The epoxy also in the center. It could be a 1 or 2 part room cure epoxy. Very good adhesion. Depends on how quickly you need to remove something. So everything is going to be varied on the actual test that you're performing. Also, we have the double back tape just to the right of the epoxy. And then we have the Blanchard glue or the hot glue, which is a little less consistent from point to point, but it is convenient to apply. Sometimes it's not as uniform as the other adhesive that you see there when you're applying it, but it is a fairly common adhesive to use. Now on the next slide here, we have the 2222C teardrop adhesive accelerometer with the various different adhesives and a combined graph to show that if used properly, you have very minimal difference in the response, provided you, again, clean the surface, make sure you use the minimal amount, and you've got a good response. So it's a good slide to see that as long as you adhere to good practice, you're going to get good response from the various adhesives. And this is out to 10 kilohertz, so that's a fairly good, very good frequency range to look at. And again, this is the resonant curve. We can see the out to 50 kilohertz with the different adhesives, and we've got a pretty good response from the different adhesives used. Fairly effective for adhesive mounting. Now this PODs test setup is just another form of mounting. It's kind of unique. It's something that it needs to be addressed in that we have a 46A accelerometer that's threaded into different pods or mounting bases. And that's important to understand that how does that affect my mount. So this is a nice design that allows easy installation and removal of accelerometers. It's a threaded accelerometer that goes into different pods or bases. And we've got 5 different versions available. And we'll show the response of the unit itself and also in a base to understand how that affects the mounting. We've got a single-axis hex stud mount, single-axis cube adhesive as opposed to stud, and then a triaxial cube stud mount and a tri-hex stud mount. All these mounting configurations provide flexibility to the user for doing different mountings. That's why we're mentioning this here. So we have the 46A results in a titanium hex base or pod, just to show the difference between the accelerometer adhesively mounted directly to the shaker and then threaded into the hex base and another frequency response run. We overlaid the curves, and you can see with the direct glue versus the hex pod, very minimal difference between the 2 units as far as the mounting goes and the response, which makes for a very nice flexible mounting scheme. Homing in on the reliability factor, we did a final test where we used 3 of these 46A accelerometers in 2 pods. One had standard coupling grease, one had never seized, and one was dry with no couplant. And we underwent a random vibration profile at 125 degrees C to test if the threaded accelerometer would back out of the pod. And we can see from the next slide the results that through the test profile we had very minimal, if not negligible, response between the different units, which provides a very good, flexible, reliable option for mounting accelerometers. What I'd like to do is go over some conclusions here, referring back to Scott's part of the presentation on the critical parameters in order of priority. With a stud-mounted unit, the perpendicularity was critical. We needed to emphasize that because we saw the most dramatic results when they weren't perpendicular. So you want to have a good perpendicular mount with a stud mount. Flatness and torque were addressed at different degrees of response and effectiveness. Center screw mounted flatness and torque was addressed. We also addressed the adhesive mounted units, and the thickness of the adhesive is more important than the material itself. As we showed with various different adhesives, we had the overlying curves. So it's a matter of using correct installation and the minimal amount of adhesive. The grease versus dry mounting, that tended to be a very important parameter to home in on for our users. The grease does mitigate a lot of mounting problems that you're going to encounter in real life. A lot of the times you cannot get that perfect ideal mount, and we know that. So it might be worth noting that grease or machine oil to put on your mounting surface will help increase the high-end frequency response. Roughness is not as important parameter as long as the grease is present, because it can take care of that. At least that's what our test has proven. Accelerometer designs, obviously the center hole mounted is less affected by the perpendicularity due to the inside diameter of the mounting screw. We have a little bit of leeway there, so that's important to understand. And new product designs such as our 46A in the pods provide flexibility in mounting configurations and allow a lot of different options to the users out there. With that, I think I'd like to just say that we have asked the experts to submit your questions for myself and Scott, and that concludes the presentation at this point. I'll turn that over to Sinan.
Thank you, Jim. And really a big thanks to both Scott and Jim for lending their applications expertise and walking us through the test results. At this time, we're going to open up the webinar and the floor to questions. We've got several that have already been submitted. Thank you very much to our audience. And we're going to kind of roll through the questions based on times that they've come in. And our first question, and I'll just throw it out to Scott and Jim, is there a recommended thickness for the adhesive layer between the accelerometer and the system under test? And does the thickness make a big difference?
Jim, you want to do that one?
Yeah, I can take that. Maybe an 1/8 of an inch to a 1/10 of an inch, roughly, if you had to do. I mean, we had 3,000 to 15,000 on a very controlled test, but yeah, you're talking about an 1/8 to a 1/10 of an inch is what you'd be looking at as far as the thickness. And
I mean,
go ahead.
Well, I was going to say you sort of had a slide. I guess it was wax, but you had a slide that proved that the thicker that wax gets, the worse your response gets. So. The general answer is the thinner you can get that bond line, the better, right?
Yep, that's it. I mean, the thinner the possible, the better.
So our next question, do pod mounts require grease for the pod mount and perpendicularity?
Not sure I completely understand the questions. Certainly everything that we've talked about still applies with the pods. You would, if possible, you want to be able to use the grease underneath the pod adapter. You definitely want to get the perpendicularity correct when you mount the pod adapter to the mounting structure. So I think that's probably the simplest answer.
Great. Next question, what is the technical role of grease in achieving a good performance?
That's a good question, and I think I see a number of variances of that same question. Essentially what the grease does is, if you recall, we talked about that very rough flatness, that 500 micro-inch flatness where you can actually see the roughness. So there are gaps, for all practical purposes, there are air gaps in between the accelerometer and the mounting surface. And if you ever look at like the bottom of our accelerometers, you'll notice that's a very fine, it's like a 16 micro-inch surface itself. So the idea really is to get any amount of damping material that might be in there, like air, for example. So the ultrasonic coupling really fills those gaps and it just allows for more surface area to be contacting the accelerometer and improves the stiffness of the mount.
Great. Typically, we perform testing between 20 and 2500 hertz. Can you show the curves in this range?
We didn't focus on that data range, simply as I mentioned, to manage the data set that was being collected while we were doing all this. So we don't have that data for all the results that we showed here. I wouldn't expect in that frequency range. I think if you recall, if you look at all these curves that we showed, they all converge down together right at about 10 kilohertz. So at least for these accelerometers that we were looking at here, all these different mounting variations didn't have much effect on frequencies below 10 kilohertz. So no, we don't have that data, nor would I expect a lot of problems in that frequency range if you don't exactly follow all these mounting recommendations. Jim, would you agree?
Yeah, I'd say you're down on the flat passband or frequency that's flat. These issues are showing up towards the top end of the frequency range of the unit, and that hence your emphasis on the resonant curve.
Mm-hmm. Next question, does roughness and flatness also affect adhesive-mounted accelerometers, or is it balanced by the mechanical filter of the adhesive?
Yeah, I think the adhesive is going to take up a lot of that, not unlike the grease.
Yeah, I would agree. You know, and most of our adhesive mount accelerometers, I suppose you can come up with an exception, but most of them aren't specified to that high of a frequency, so it may not make a lot of difference. But yeah, essentially, it's performing just like the grease.
Yeah, you're gonna get Scott. You know, let's say you look at the 2222C out to 10 kilohertz with a nice flat, you know, cyanoacrylate adhesive, a thin mount, and I think it's data showing we have good response out there with that adhesive.
Next question, is the recommended torque valve on the technical data sheet that is supplied with the accelerometer?
Yeah, is the recommended torque value specified on the data sheet? Yes, hopefully it is. If you can't find it on the data sheet, call us, but it should be there. It should be there.
It's on there under the environmental, I think, or the mounting.
Another question, looks like just a question on an acronym or abbreviation, TIR. Can you please explain that?
Yeah, TIR is total indicated runout. So when you're wanting to specify flatness, you would actually use a dial indicator on a reference surface, and then you would run the stylus on that dial indicator across the surface, and if you want it to be perfectly flat, you would not look, you know, the needle deflection on the dial indicator shouldn't move. So TIR is total indicated runout.
Great. Another question, for mounting of accelerometers inside high temperature water environments where grease or wax or glues or epoxies can't be used, does that just mean that the advertised sensitivities will not be obtained?
You know, I won't say that the advertised sensitivities won't be obtained. Will you have a high frequency issue potentially? Yes. I remember, bear in mind again that a lot of what we're talking about is stuff going on at high frequency. A lot of these parameters that we talk about achieving the flatness, achieving the roughness, are issues that are happening at high frequencies. So will you achieve the advertised sensitivity? Yes. At lower frequencies, yes. But you really do need to be looking at how high in frequency are you attempting to measure, you know, and if you're not looking at anything, say, above 5 or 10 kilohertz, I don't think it's a worry.
I would just like to add on there also that the environment here we're talking about might direct you to, you know, a fixed rigid mount, high temperature water environment. Just the environmental part of the question.
Yeah, that's a separate issue, yes.
Another question, we do shock and impact testing at our company. To prevent the accelerometer from ringing loose, can we use adhesive with stud-mounted accelerometer? What would be the effects?
That's a good question because shock impact testing is, for all practical purposes, mathematically, is high-frequency testing, so that the mounting issues do actually become quite important. Certainly,
And
yes. If you want to go ahead and use an adhesive on a stud-mounted adhesively mounted as well as stud-mounted, I don't see a problem with that. It couldn't hurt, right,
well,
Jim?
yeah, and I'd like to add to that. It's also actually recommended that you do that because after the shock, if you've seen a crack in the adhesive, you know you had something come loose. So it's a good indicator at high G shock to do both.
Is the drying time for an adhesive hardness an important factor in mounting the accelerometer for calibrations? Wax versus superglue.
Well, certainly wax, I don't think there's a drying issue there. Superglue, absolutely. You'd have to refer to the superglues, their manufacturer's recommendation, but yeah, I certainly wouldn't superglue something down and then go do a test while it's still curing because, yeah, you want that superglue to harden up first. So I don't, what's the cure time for those things? Minutes?
Yeah, I could add to that on the manufacturer's data sheets. They recommend certain things, and they tell you how much more tensile strength you'll have after X amount of minutes. They're virtually instant adhesives for this cyanoacrylates, but they do get stronger as time goes and cures. So we're talking 45 seconds to a minute to 3 minutes now. You're at the highest strength, or you can go higher, but I mean, most times you're talking about under a minute to cure, and then go ahead and do your calibration.
The next question, if you have accelerometers with a resonance frequency around 12 kilohertz, for instance, are the results of the test about roughness, flatness, angle similar as far as the reduction or shift of the resonance peak, or does it not significantly affect the results due to the fact that the resonance frequency is quite low?
What do you think, Jim?
I'm trying to read the question.
Well, essentially they're asking if I've got an accelerometer with a resonant frequency in the 12 kilohertz region, do these effects still apply? I guess I've never thought about it being that low.
Well, you just mean that you have a lower resonant frequency, and so now you're wondering, does this apply because the other ones were at 40 kilohertz, let's say, or higher as a resonant frequency? I think it would still apply because it's just a different Q or transmissibility issue.
I would tend to agree. I mean, I guess I got to think about that one, but I think you're right. I mean, what's the difference between it being at 12 kilohertz and being at 40 kilohertz? I think you're still going to see the effect.
Yeah, it's a response of the input to the output to the input. So it's
well, yeah, and now that I think about it, for an accelerometer to have a resonant frequency that low of 12 kilohertz, that means
pretty high sensitivity.
It's pretty high sensitivity, and it's probably pretty big and heavy. So yes, I would say these effects, of flatness, roughness, etc., would probably have an effect on them. Yeah, now that I think about it, yeah, absolutely.
Looks like I can kill a couple questions at once here. Talking about grease, what to do in high temperature areas, and is there any specific grease you would recommend?
So for a specific grease, it's essentially the same ultrasonic couplant that they use for sonogram tests. I know that doesn't help, but I think if you Google ultrasonic grease or sonogram grease or something like that, you should be able to come up with one. I can't think of the brand that we use. Interestingly, though, we didn't talk about this, and we don't have the test results, but based on my personal experience, even something like a light machine oil will work just as well. So something like, I think it's called 3-in-1 oil from Loctite, that works just as well. Any kind of light machine type oil will work. Even just, grease, like you grease your bearings on your car, should work. For high temperature applications, gee, I don't know. I guess there's got to be high temp greases out there, right? Jim, I don't know. Are there some rated that high?
Yeah, I'm sure you'd have to Google that and see yourself and see what's available in the market.
How much would it affect a measurement, the fact that the accelerometer surface is not 100% in contact with the surface under test? Accelerometer surface over circular part, for example.
You want to have as much surface contact area as possible.
Yeah, that's an interesting question. I don't know that. I mean, yeah, Jim's right. That would be an interesting test, actually. I think what they're asking is
the radius.
As long as it's concentric, and if you, as you start to lose surface area, does that have a bearing on the performance? I would say probably yes.
A possible solution to that would be maybe some machined ceramic or something lightweight that's stiff that has that shape, and use it as an intermediary mounting fixture that limits the amount of damping and still have the surface area.
That might work. You want to make sure that intermediate part that you use doesn't cause more problems than it
right.
solves. But you know, a ceramic would
a special circumstance. Yeah.
Yeah.
So we're about 10 minutes from concluding our webinar. A few more questions for you gentlemen. And a lot of the questions that are coming in relate to the presentation itself. It seems like many people want a copy of the presentation or some of the graphics inside. As a reminder to our audience, this presentation will be sent to you in recorded format following today's webinar via email. The next question is, I've been using a piezo accelerometer not exactly considered for horizontal use. What distortion or eventually damage of the sensor can I expect?
Interesting, Jim. I don't know what kind of piezoelectric accelerometer would not be considered for horizontal use. I've never run across that.
Well, we've got crash testing. I guess I would just ask, is that within an ATD or dummy, or you're on just, I mean, the 7264 and the 7231 are typically used in the crash dummies themselves, and they have specific mounts and so forth, so I'm not sure where the question's going.
Well, there are certainly devices out there known as geophones that have a mechanical movement inside of them that are suspended by springs, and those would, you know, they actually have special versions of those that are designed for horizontal applications, and some designed for just vertical applications, and some very stiff ones that are designed for, like, you know, 180 degrees, any point. I'm really not aware of a piezoelectric accelerometer that couldn't handle any angle.
Yeah.
Just because a piezoelectric accelerometer is a very stiff sensing element, so that's an interesting one. Not sure I have the complete answer for that one.
Mm-hmm.
Next question. We use model 7264 and model 7231 accelerometers for automotive crash testing. We have occasional resonance on some of the crash dummy channels and vehicle channels. We do not use ultrasonic grease. It sounds like that may likely help. Would you agree?
I think I would, Jim, huh?
I'd say there's a lot of variables there, but it's possible, but I'd be very hard to say yes or no on that.
What frequency range do the wax-based adhesives work optimally?
I can tell you on that, it's going to determine the area of the wax, the amount, the weight of the accelerometer, but certainly at lower frequencies, say below a few kilohertz for the wax. But it depends because, you know, there's calculation based on the resonant, how it changes the resonant frequency of the mount. And that's the area of the wax under the accel, as well as the thickness and the modulus of elasticity of the wax. So, I mean, I don't know if you come up with a number that's valid, but certainly it's for lower frequencies as opposed to extremely high frequencies.
Got it. Under non-laboratory conditions, when are specific adhesives more or less useful?
I guess that would really depend on the application, right, Jim?
Yeah, temperature, I would say, would be a key, and also the size of the unit, the weight, the mass, which is most appropriate.
Does the pod system offer any advantages to commonly available nut-type mounts?
Glad you asked that. Yes, the pod system, of course, is new and unique, and it certainly allows, you know, the big advantage that it has is you can invest in a relatively small number of sensors and then a very wide range of very inexpensive mounting adapters. So that's the whole idea behind that as a test engineer, you can approach a whole wide variety of potential installation situations, and yet you really only have one sensor type that by the way, can be just calibrated in one way. You don't need all these different, right angle connectors, top connectors, hex mount, triax, etc. You just need to keep that one sensor type calibrated, and the mounts come in right when you do the test. Does that sound right, Jim?
Yeah, it sounds.
And looks like our final question for the day, are there accelerometers with resonant peaks higher than 40 hertz?
Absolutely, yes.
Absolutely. What is it, our 7259B is actually
rated. And the 7240 charge type, and then the isotron version. Yeah, they're like 90 kilohertz or something.
90 kilohertz. So absolutely.
We have other high G shock accels with much higher resonances also, but those are more for high G shock, so it depends on the application.
Yes.
But yes, the answer is absolutely yes.
Looks like another question popped in. Are there accelerometers in one pod for redundancy?
Yes.
Yes, I think the question. So, yeah, I think the question is related really to that when we showed the triax and the what we call the tri-hex.
Yeah.
So yeah, redundancy could be one reason why you would want to mount all three accelerometers in the tri-hex. The other reason is because you have, one mounting device, one mounting adapter there, and yet you have all these different sensor types. You could actually put different full-scale range sensors on there. So, accelerometer number one might be 50 Gs, the next one might be, 500 Gs, etc. So there's different full-scale ranges that you can put in there, and that might be really valuable depending on what you're trying to do. But certainly redundancy is another good reason for doing that.
Great. Well, it looks like our final question, Scott and Jim. Fantastic facilitation by both of you. Thank you very much, and also thank you to our audience for dialing in. There may be a few other technical questions that were not answered that we'll be following up with you on email, and certainly we have Scott and Jim's email addresses displayed to you, so please feel free to utilize them as resources to you. At Meggitt, it is our objective to help you grow your business by answering some of these questions, and we hope this information has been valuable to you. There's a vast amount of resources on the website at www.endevco.com, which can help guide you through the next webinar presentation, and feel free to vote on a future topic that interests you. Your feedback is invaluable for us as we develop the next series of webinars that will be coming to you in the next few weeks and months ahead. So with that, we do appreciate your time, and we'll be back in touch via email. And please, again, take a moment to vote on our next poll on the future webinar you would like to attend. We've got it displayed right now, and at this time I will conclude the call, and thank you again.